What if I was to tell you that a lump of uranium metal the size of your fist contains more explosive energy than 1,000 tons of TNT? And yet it doesn't just blow up. And that's kind of strange. Why doesn't it just explode in your hand? Well, that's the power of nuclear fission, the splitting of uranium nuclei. But how does this violent reaction get tamed inside a nuclear reactor? In this video, we're going to look at how do you split the uranium atom, how do you stop it blowing itself to pieces, and how do we get so much energy from such a small amount of material? Uranium-235 is what's known as a fissile material. This means under the right conditions, you can force its large nuclei to split into smaller ones, releasing a whole pile of energy. But that's not the weirdest part. It sounds complicated, but in essence, all you need is some uranium, some cold water, and some flipping clever engineering.
Let's look at the core reaction. A slow-moving or thermal neutron strikes a uranium-235. If it's absorbed, the nucleus becomes 236, which, just like a tower of blocks, is unstable, and so it splits into two smaller nuclei, throwing out 3 neutrons in the process.
If you add up the mass numbers on both sides of the equations, you'll see it's different by 3. This tells us the number of neutrons. And now we get to the tricky bit. These neutrons that are emitted are flying far too fast for them to be absorbed by the uranium-235 nuclei. Therefore, we have to slow these neutrons down, and this is done using a moderator, which is normally made of water. After several collisions with the water molecules, the once fast-moving neutrons have slowed down sufficiently for them to be able to interact with other uranium-235 nuclei.
It's like snooker, where balls of the same size share their energy. So
we are now on the verge of the infamous chain reaction, but what stops it from getting out of hand? Enter the control rods. These rods, made of boron, are able to be moved up and down between the fuel rods, and they're good at absorbing or sucking up slow-moving neutrons. In the famous Homer Simpson scenario, you simply lower the fuel rods down as far as you can go and run like hell.
But where does all this energy come from? When we compare the masses in the equation, the numbers don't match. The products have mysteriously lost mass.
So where did this missing mass go? Well, according to E = mc squared, there is no missing mass, it's just transformed into energy. Albeit not very much per reaction, but given that there are billions upon billions of fission reactions happening every second, it adds up to an astronomical number of joules. So that is nuclear fission, a reaction that is tamed by a moderator, controlled by control rods, and powered by a tiny but mighty change in mass. And if you thought that was interesting, check out this video on nuclear fusion, the power source for our energy in the future and one that powers the stars right now.